Log on, tune in, find out. Another good idea from Cambridge.
Okay, thank you, Peter, and thank you to the organisers for asking me to give this talk today. So I'm going to be talking about weighted space filling designs, where we want to not only fill our input space, our design space, but we want to take account of essentially soft constraints we've got going on. So we think there are some areas of the design region where we're more interested in exploring than some others. And this is joint work with Veronica Bowman from DSTL. So I'll start by looking a little bit about the background and an example of an experiment from dispersion science which actually sort of motivated this work. Then we'll get straight into thinking about how we can incorporate prior information or essentially weight functions on our design space into our design selection. And then we've got a variety of examples, some toy examples, and we'll go back to our dispersion example. And when we look at the examples, one way we'll assess the designs is through some graphical evaluation techniques that we've been looking at. And this is still work in progress, so we're interested to hear any comments or suggestions that you might have. So this is our motivating example. And so when you've got a dispersion model, the aim is to try and understand and predict the downwind hazard that's generated by a chemical or biological release. So our dispersion model, each run of our dispersion model tends to produce a 2D plot of dosage like this. So here, essentially what's going on is that we have some source that's released somewhere down here. We have a wind direction which is essentially like this, and it spreads our agent across this area. So this is a geographical region, and the input factors to the computer code that would generate this would be things like the wind speed, the wind direction, other met variables like cloud cover, and things to do with the source that was actually the source of our agent, so its mass, its location. So there's a wide variety of applications. There's the obvious applications that you might get in accident response type planning. These kind of things were used when people were trying to understand how the volcanic ash from the Icelandic volcanoes was going to disrupt flights. And there's a variety of different models that can be applied. There's some very simple Gaussian plume type models where you can basically write the equation down, and there are some rather more complicated Lagrangian type models where your computer code will take some time to run. And the application that got us thinking about this was in terms of sensor placement, and we were interested in, well, our collaborating scientists were interested in trying to decide where to put sensors in the real geographical region in order to be able to accurately detect a dispersion. So we're not going to talk about the sensor placement problem, but we're going to think about some methods that can help perhaps underpin that. So when we started talking to the scientists, what they were doing for their sensor placement is they had to get a representation of the dispersion model into their sensor placement tool. So what they did was 80,000 runs of their dispersion model, the computer model, and then they looked at the average number of plumes that each location in this XY grid actually saw. And they ended up with a surface that looks something like this, and then it's this that they plugged into their sensor placement tool to represent their dispersion. So what we want to do is try and see, can we basically help them get down to using rather less than 80,000 computer model runs to try and do this problem. So there are some particular characteristics of dispersion modeling that made us think about some of the things we wanted to do. So our input variables to the model are usually of two types: meteorological variables, wind speed, wind direction, etc., and source variables, so the mass, the type of agent. And they can be either quantitative or qualitative. So we have both types of variables going into our computer model. Now the interesting thing is there's a substantial amount of prior information about these input variables, about how they vary. So if we're looking at a particular scenario the scientists are interested in, there'll be historical meteorological information we can get on wind speeds and wind directions, for example, and they'll know the type of release they want to investigate, the type of agent, a likely range of amounts of the agent that will be released. And these prior distributions, this prior information we have usually isn't going to be independent. So, for example, within the Met variables, wind direction and wind speed is very rarely independent. It usually comes via windrows. And also, if we're looking at between the meteorological variables and the source variables, they won't be independent either. If we're looking in a plot like this, if we're really interested in what's happening somewhere down here, and our release is here with this kind of wind speed, that's obviously not going to be terribly interesting to us. So there are dependencies in there as well. So what we end up with is essentially a joint probability density, or we're just going to think about it as a generic weight function across our design region, which tells us how interested we are in different areas of the design region, and is likely to have substantial areas with very low weight or zero weight, where for one reason or another it really isn't that interesting to take a run of our computer model. So this is an example of the type of prior information that we might get. This is windrows. So this is just saying that for this particular example, most of our wind is over in this direction with these kind of strengths. So we could run our computer model with different direction winds at different strengths, but it wouldn't really tie in with the scenario that we're looking to investigate. So what we're going to try and do, as I say, is reduce the number of evaluations of the model that are needed, and we'll do it by trying to develop a class of criteria for constructing these space-filling designs that take account of these relationships between the variables and the prior information we have on those. And we're going to evaluate the designs we get in terms of both their sampling properties, in terms of these distributions, and their space-filling properties. And we'll do that using some graphical methods. So one of the underpinning things is going to be this idea of a weight function, which you can think of almost as just a probability function across the design space. So it's going to be greater than or equal to 0, and it's obviously going to depend on the problem we're looking at, depend on the scenario the scientists have defined, or the historical data we have for the meteorological variables. Something I've been trying to think about recently is I think we can almost think about this in terms of a fuzzy set, where if our design region is curly x, then we can have a fuzzy set which takes the elements of curly x along with our weight function, which would be the unnormalized membership function for the fuzzy set, and then I think we can think about this as doing space-filling designs for fuzzy design spaces, which might be an interesting way of thinking about the problem. But however we think about our function w, it's clearly going to be a positive function which tells us how interested we are in different parts of the design space, wherever that's come from. So we've heard quite a lot in the day and a bit already about space-filling designs, but essentially we're looking to find a collection of combinations of the input values which provide information or attempt to provide information about all the relevant regions of our design space. And there are lots of different types of space-filling designs. The ones we're going to focus on are going to be thinking about either spreading the design points out as far as possible across the design space, or covering the design region as evenly as possible. So I think we can think about these as being maxi-min designs, maximizing the minimum distance between design points, or mini-max designs, minimizing the maximum distance between our design and our design region. Repeat points aren't space-filling, so these designs, space-filling designs, are often used for deterministic computer models where repeat points aren't going to give you any extra information. They don't depend on a particular statistical model, and they typically then used with non-parametric regression models and allow a variety of models to be fitted. And as I said before, there are lots of different types. We've just heard talk about Latin hypercubes. We're going to be thinking about these distance-based designs, which are either going to spread the design points or cover the design region. So in order to apply these types of designs to the problem that I've described, we have to extend it in a couple of ways. The first is we need to include qualitative variables in our design. That's a fairly minor extension. And then we need to include this weight function, which tells us about the relationships between our input variables. So to set this up, let's say we have K1 quantitative variables and K2 qualitative variables, with the jth qualitative variable having mj levels. And then we can define our distance metric between 2 points in our design space as essentially a weighted sum between the Euclidean distance in the quantitative variables and a 0, 1 distance in the qualitative variables. And this weight alpha, so this is the indicator function clearly. So if the two runs are the same on one of the qualitative variables, that will give you 1, otherwise it will be 0. And we have this weight alpha, which just lets us adjust the relative importance we give to the quantitative and qualitative terms. It can help us adjust for differences in scale, for example, between the different variables. And this clearly is going to work for unordered categorical variables. For more complicated categorical variables with more structure, like ordered categorical variables, you can define some similar types of distance metrics to put in here. So then, how are we going to find our designs? Well, we're going to use computer search to minimize a couple of different objective functions. So for the second, if you just ignore the w's which are in here, which are our weight function, without the w's, these are the standard objective functions you would get for coverage or mini-max and spread or maxi-min designs, as they were defined by Johnson and co-authors 20 or so years ago. So what we've got with the coverage designs, what we want to do there, remember, is we want to make sure that any point in our design region is as close as possible to a point in our design. So we look at taking the average across the whole design region of, you can think about this as the distance between our design and any point in our design region. We define that, the distance between a design and a point, as being the distance, the smallest distance between a point in the design and the point we're looking at in the design region, which is why we have the minimum in there. And then with the spread designs, what we're looking to do is minimize the sum of the reciprocals of the distances between the points in our actual design. That will spread them out as much as possible. So we can complicate these things by weighting them up. We'll just put these equal to 1 all the time. But what we are going to do is we're going to multiply our distance metrics by our weight functions to try and adjust how we do our space filling. So you'll see what we've got in here for the coverage, rather than just looking at the minimum distance between our design and every point in our design space, we actually look at the minimum weighted distance in there. And with our spread, we actually look at the weighted distance between the points in the design. But you'll see the difference is we only look for the coverage, we just weight it by the point we are comparing to in our design space, whereas with the spread we put the weights in for both points in the design where we're working the distance out between. If you don't do this in the spread, if you just think, oh, I'll do the same as this, and essentially just use one of the points, you can get some very strange designs that are neither space filling nor actually correspond very well to your probability distribution. So thinking about these two slightly more, why does this work? Well, for coverage designs, we clearly want to attract our design points to relevant areas of the design region. And so the converse of that is essentially we want to make sure that any points which have 0 or low weight are not going to be space filling. And so if you see, if any point has weight 0, then clearly the minimum weighted distance between that point and any design you come up with will be 0. And so including that point in your design can never improve its space filling properties under this criterion. So those top points just won't be included. For spread designs, we want the design points to repel away from each other, and what we get is as the weight goes to 0, this reciprocal distance obviously tends towards infinity, and again, that means those points aren't going to be included because any point they're already as far away as they can be from any point in our design. So by putting these weights in, we're essentially enabling us to adjust our definition of space filling to take account of these dependencies. So we'll find our designs, we'll minimize these objective functions using computer search. The small examples we've done at the moment using a row exchange algorithm, and if you want to, you can put things in there like nearest neighbor constraints to try and speed it up. If you've actually got a big example, I think coordinate exchange variant would be faster, where you do a little continuous search to decide on each coordinate. However you do this, you don't want to be recalculating all the distances every time. That would be a nightmare. So in the row exchange, you can calculate all your distances up front. If you're doing a coordinate exchange, there are efficient ways of updating the distances to speed up the algorithm. When we did a row exchange, we used a quasi-random number sequence for our candidate list, and we also use quasi-random numbered sequences to approximate our design space. For example, oops, let's just go back. For example, when we have to approximate integrals like this, we use a quasi-random sample for that. So how else could we think about this problem? Well, one obvious way is to take some IID, random or quasi-random sample that doesn't take account of these distributions, these dependencies, or a space-filling design that doesn't, and then transform it according to the distributions that we've got. So when we come to our examples, that's one thing we're going to compare to. We'll take a Latin hypercube sample, we'll transform it to match the marginal distributions from our weight function and get the pairwise correlations as close as possible. And of course, there's lots of work on design spaces where you actually have hard constraints in your design region. And there's a recent paper in the context of constrained optimization by Kleischen and co-authors where they look at constructing Latin hypercube space-filling designs for hard constrained regions by essentially generating unconstrained Latin hypercube designs and keeping the points which stay in the constraints. So we'll have a look at this one when we come to some of our examples. We're also going to do some graphical design assessment to actually compare our designs. So we'll do a fraction of design space plot. So these have been used a lot when we're thinking about response surface designs and variance, prediction variance, but we're actually doing a fraction of design space plot with respect to the distance metric. So we want to know what proportion of our design space is within what distance of our design, and that's kind of reflecting the coverage properties of our design. And we'll also look at what we've called fraction of design point plots, and that's going to be with respect to our weight function, our prior distribution, and that's going to say what fraction of our design points have a particular weight attached to them. So that's going to think about, this is thinking about the space filling properties, and this is thinking about essentially the sampling properties. And the weight functions we'll use in our examples, well, in each case we'll assume there is some prior distribution which has come either from historical data or from subject experts about their interest in the design space. And then the two weight functions we'll consider, the first one just uses that prior distribution, and the second of these transforms the prior distribution with two tuning parameters, alpha and gamma. That was suggested by Joseph and co-authors, and that essentially allows us to tailor our weight function depending on how much we actually sort of believe our prior distribution. And we can actually come up with some very different designs from these different approaches, and the designs can change quite a lot as we change alpha and gamma. So I've got three examples, two toy examples, one with just two quantitative variables and our weight function, our prior distribution is just a logistic function. And I've got a second example with two quantitative variables and one qualitative variable where the weight function conditional on the qualitative variable is bivariate normal. And then we'll go back to our dispersion example where we've got 7 quantitative inputs. So, I don't know how well you can see these. Hopefully you can see them a little bit. So what we've got here, each of these panels gives us a different space filling design. So I'm actually going to start down with this panel because, ignore for the minute the contour plot. You can see the dots here. That is the completely unweighted coverage design that just tries to space fill the region. And then in each of the panels, obviously, sorry, this is x1, this is our first factor, this is our second factor, so these are our points, this is our design space that our points are filling. Each panel then gives us a different space filling design, and the contours give us the weight function that tells us our interest in different regions. So if we go back to this panel here, this is the first weight function where we just use this logistic function as our weight, and we can see that the design points here are basically spread out along the ridge. They're space filling the ridge of high weight of the area we're interested in. Then these two plots give us designs from the second weight function with different values of alpha and gamma. So we change gamma here from 1 to 0.75. And what we can see is that the second weight function is tending to actually want to put a lot more points near the maximum of the weight function, and many fewer near the and a few points further out to try and space fill. So what you actually get, whereas under the first weight function we sort of space fill in the high weight areas, the other weight function ends up wanting to have lots of points in high weight areas and then a couple of points to do space filling further away, and that becomes a bit more extreme when you have a change gamma, so we have points in even lower regions, lower density regions. So here are our fraction of design space and fraction of design point plots for those designs. So let's look at the fraction of design space first. So this is thinking about the space filling properties of our design, and I don't know if you can tell the colours. This line here, the lowest line, so on this plot you want the lines to be low, because that's telling you that most of your design space is within a very small distance of your design. So the lowest one is just the coverage design, the unweighted coverage design as we'd expect, and as we change the weight function we can decrease the space filling properties of the design. So weight function 1 is the red line here, for example, but of course we trade that off by improving the sampling properties of our design in some sense. So over here in the fraction of design point plot we can see that this line is the coverage design, the unweighted coverage design, and most of the points actually have very small weight. So you're not necessarily sampling in areas that you're particularly interested in, whereas the red line, which was our weighted coverage design, has much higher a much higher curve. So this plot, high is good, this plot, low is good. And it's going to be a trade-off between the two. We can do exactly the same thing with spread. I don't want to spend too long on these, except what I would say is that the spread criterion, as you'd expect, even with the weighted versions, the points get a bit more spread out. This is the unweighted spread design, and you can see that the points, many of the points are right on the edge of the design space. And obviously, once we take account of the weight function, that no longer happens, but the weight function 1, just using the logistic function, still puts them on the ridge, whereas if we then transform it somewhat, we get again points clustering and points being thrown out to the edges. And we can look at the same type of plot to compare these designs, but more interestingly is probably to compare the coverage and the spread designs. So here we can see that we've got the coverage designs tend to have lower lines in our fraction of design space plot, so they're performing better under coverage than the spread designs, which is what you'd expect, but they tend to be, in general, slightly lower on the fraction of design space plots. And these designs, of course, are the unweighted designs, which aren't taking account at all of the weight function, so they tend to perform quite poorly when you look at that. Probably going to skip the second example and jump straight to example 3, which is thinking about applying these methods back to our motivating example. So the data we've got at the moment for this doesn't have any qualitative variables. This is still work in progress. We want to run an example which has qualitative variables as well as quantitative variables. What we have got is 7 quantitative variables at the moment: wind speed and direction, the cloud cover, the x and y location of the release, its mass, and the time. And we've got this prior information from which we can construct our weight function, which is based on past data for the meteorology and essentially opinions from subject experts on the scenario they're interested in for the source. And when we combine that, we get this that essentially defines for us a release scenario. So what we want to do here, so the way we actually construct these weight functions here typically has to be empirically, because we don't have closed forms of these things. We have to construct empirical distributions from, for example, the meteorological data. So we'll compare our weighted space filling design just with the first weight function, where we just take the probability density that we construct as our weight function, and we'll compare that to doing some Latin hypercube samples which are transformed to try and match that distribution. So we can compare again coverage designs, spread designs, and our Latin hypercube design, and essentially what we've got here, I'll show you first of all the Latin hypercube design, and our fractional design space plot is this black line. So in terms of space filling, at least across the whole region, we haven't looked at the projections, so we're being slightly unfair on the Latin hypercube, but it's not doing as well as many of the, particularly the weighted coverage design, which is this red line, which is actually nearly indistinguishable from the unweighted coverage design. So in this example, we really don't lose very much space filling by taking account of the weights. But we do gain a little bit in terms of our sampling properties. So again, this red line is our weighted coverage design, and it's significantly higher than the unweighted coverage design, which is the blue line. So we're sampling more interesting regions of the design space, but we're not losing out on our space filling. So this is projections of that coverage design into 4 of the variables, and you can see that there are areas where we just don't explore in the wind speed and wind direction domain, because that's not in the scenario, essentially, the distributions that were defined by the past data. And we can just think about some preliminary results we've got here. So we've constructed the same average surfaces as we had from the 80,000 runs from the Monte Carlo study, and we can see we're getting basically the same shape. We're obviously not as smooth, we haven't got as many runs, but if we compare the squared errors to, so these were based on 200 runs either from the weighted space filling or the Latin hypercube, and if we compare that to 200 Monte Carlo runs, then we are at least an order of magnitude better in the squared error, and also our weighted coverage design is better under mean squared error than the Latin hypercube design. Okay, so we've looked at some flexible criteria for finding space filling designs where we can incorporate this weight function, and we can trade off between trying to get areas we're really interested in and still trying to do some space filling. There are lots of other applications, perhaps including an interesting idea is looking at spatial experiments where there are perhaps covariates. So you might, for example, be more interested in a physical spatial experiment in taking observations in areas where there's high population density, and this could be used in there. And something that's interesting is when we have strong prior information, we're essentially reducing the effective size of our design space, and that probably makes space filling easier than it would otherwise be in very high dimensional space. Okay, thank you.
Any questions?
Questions?
Yeah, your weight was defined on the probability of a scenario occurring, I understand. Now, wouldn't it be interesting to do the next step? And the weight is actually on those scenarios that lead to disaster. So move from the input space to the output space. And that takes you to importance sampling, I guess.
Yeah, no, that would be so. So yeah, I mean, you would have to have some quite good, some further prior knowledge that how your inputs link to your outputs. I think to do that.
Yeah, that's not easy.
But
it probably has to do dynamically,
yeah,
sequentially.
Yeah.
Yeah. Okay.
Can I just follow up on that point? Because if I were a client, I would be worried about the sort of fail-safe nature of some of the designs. That, if you for example, in your plume example, you put too much weight where you think the plume is, and then the wind is in a different direction, the plume goes somewhere completely different, then I, as a client, would want to know, well, what happens then? Can you give me some guarantee of what the fail-safe recovery actually is?
I agree with you totally if we were actually suggesting these designs. I mean, because what we're doing is we're doing computer runs of the dispersion. So we aren't actually saying, let's put points here to detect anything. We're saying, let's explore essentially explore different dispersion scenarios. So it's not that we're saying, this is the truth about the dispersion. We're saying, what happens if it's something like this? And then I think that's up then to the subject experts to come up with reasonable. But if they really don't have much prior information about it, then you'll go back to something that's much more like a straight space filling design.
So David, with the use of the weight function and setting weights equal to 0, can you use this to kind of create space filling designs for very bizarre shaped regions?
You could do, yes, yeah. And the other thing you might be able to do, we haven't thought at all about whether these designs would be useful for actually doing for actually trying to fit anything to them. So it could be that they're actually hopeless for that, or it could be that you can actually use the weight function to reflect some properties of the performance of your design with respect to your Gaussian process or what have you, to try and include that as well.
So the experiment results didn't look too good when starting with a Latin hypercube and then transforming it. Did you start with Latin hypercubes that had good space filling properties?
It was a Maximian Latin hypercube, yeah.
So do you have some intuition for why this isn't doing as well?
Well, I think it's not dissimilar to what Boshin was saying, that looking just at the margins doesn't guarantee you the joint distribution. And although we tried our best to get the pairwise correlations as close as possible, within the size designs we were doing, you can't get them exactly, and you're still ignoring the sort of basic structure. That you're throwing away some of the structure which the other weighted space filling designs had.
Nice talk, David. The MSEs that you were showing at the end are sort of a bottom line, and it so shows that you can have great gains. On the other hand, if you were to use a Maxi-Min Latin hypercube, you would think in areas where you hadn't, a large amount of weight, that things might be worse. So the question is, how did you explore at all? How, if you misspecified the P and actually what you wanted to predict was away from it, how bad things could be for one versus the other?
That's I mean, there's all sorts of issues of robustness, and in terms of also thinking about. Particularly with a problem like this, you're often more interested in errors one way than the other and things. So yeah, there's lots of ways we can extend how we're actually doing that comparison.